In today's lecture, we are going to explain the polyelectronic atoms, which are atoms having different, like a lot of electrons, and in the same instance, they are also exhibiting characteristics of a hydrogenoid. So we say the hydrogenoid is an atom that is similar to hydrogen, but has one electron. That is, okay, when I say similar to hydrogen, I mean it only has one electron in the outermost shell. So we can have hydrogenoids of different elements, that is from the periodic table. An example I usually give is calcium, because calcium among elements that you guys have learned so far is the one that has the highest number of electrons. That is from number 1 to number 20. But of course, there are those that are higher than calcium. So I always give calcium as a reference because it has the highest number of electrons as compared to the rest on the top 20 elements. So when calcium loses 19 of its electrons, it's going to have one electron in the outermost shell, and you're going to abbreviate the atom of calcium in this way. Let me just show you. You're going to say calcium 19 plus. So because calcium is a metal, so it's going to lose electron. So this here is called a hydrogenoid of calcium. So in the polyelectronic arena, we are going to look at atoms having a lot of electrons, as the name states, polyelectronic, having a lot of electrons. Then we are also going to look at the hydrogenoids as references. So resolution de la equation de Schrödinger. So Schrödinger's equation, which is represented by H psi, is equals to the energy. So the H here is a Hamiltonian operator. Hamiltonian operator. So the Hamiltonian operator stands in for the kinetic energy and the potential energy of the electron. Because we said Schrödinger's experiment, or Schrödinger's explanation of the atom, is based on the probability idea. He states to say that an electron is found in different positions at the same time, which we are calling quantum superposition. Therefore, for us to determine the position of the electron, we are supposed to measure or find out what its probability is. So in the case of finding its probability, we are supposed to take factors into consideration. We are supposed to take the factor of kinetic energy. We're also supposed to take the factor of potential energy, because we know that in a system, energy is created in different forms from one form to the other. So that is to do with this equation here. So la resolution de l'équation de Schrödinger, you guys don't do the resolution of the equation. So then we are going to look at the approximation orbitale ou bien monoélectronique, la notion d'effet d'écran, fonction propre monoélectronique, the diagram energetic. So what we are going to concentrate on this chapter is diagram energetic. But I will still explain how these things flow. So notion de effet d'écran. This is a principle that explains the shielding energy that electrons exhibit towards each other. Like when you have an atom, just represent it with something. Say we have sodium, like that. Sodium is in group what? Sodium is in group what? Guys, mkaina two.
Isn't it in group 1?
Yeah, it's in group 1. Yeah, so the notion d'effet d'écran is basically the shielding energy that electrons, because you know when you are removing an electron, from this atom here, when you're removing it, what do you call that process of removal? Like you're removing an electron from an atom. What do you call it?
Ionization.
Exactly, it's called ionization. So in the process of ionizing an atom, because ionization is the gaining and the losing of electrons. So when an atom loses electrons, it forms a positive charge, and that's an ion. We call it a cation. That is for metals. Then when it gains an electron, it forms a negative charge, and that is what you call an anion. So that is for non-metals. So when you are in the process of removing an electron, there is always a nuclear. There is always a nuclear force there is always a nuclear.
Group
No,
one.
group one. Group one.
Must be his network.
You have a question? Who was that? You have a question? Okay. So, like I was saying, so when you are removing an electron, or in the process of ionization, because we know that ionization is one of those processes that requires a lot of energy. In the process of ionization, it is found that the nucleus possesses an amount of energy on these electrons. So when you look at the potential energy or the nucleus energy, Z here represents the nombre charge effective. It represents the noyon, of course. So when you look at the potential energy that the nucleus possesses on these electrons that are in the first shell, as compared to the ones in the third shell second shell, and the last ones in the third shell, the energy that you require, the energy that will be required for you to remove this electron, the energy that is going to be required for you to remove this electron here in the in the zone of the nucleus will be higher as compared to the one that you are going to use to remove the electron in the outermost shell. Now, what's the case? So because we know that from Bohr's theory, we explained that electrons are always found in stationary energy levels. They are found in stationary energy levels. But when you come to explain that with Schrodinger, it is disqualified because it does not explain the quantum part of the electron motion. Now, we're using Bohr's principle, of course, we are going to build from that. We're saying electrons are found in stationary orbitals, isn't it? Now, if they're found in stationary orbitals, what's making them stationary in those orbitals? It's the nuclear energy that is found in the noyon or the nucleus. So the nuclear energy is what gives these electrons their position. They are stationary, like what Bohr stated. Their stationary positions are are deduced to maybe say they are how can I say it? They are affected by the nuclear energy that the nucleus possesses. So effect the cron comes in when because effect the cron is like screening energy. So when you are removing an electron, there's a representation here, I think. Like when you are going to remove an electron, in the process of ionization, you are going to have a screen effect. You're going to have a screen effect. Like how can I put it? Like you are watering a garden. You're watering a garden. So the first way is watering a garden. When of you like on a plain ground. Now the other one would be watering a garden. Now you have a plastic on top. Now the plastic is going to be like the shield we're talking about here, because this is called the shielding effect or the screening effect. Selamium shows. So there's going to be a shielding effect that the nucleus and the electron you're seeing here, that this electron and the nucleus are going to possess. There is that energy that is going to be possessed by the nucleus, and there's going to be a repulsion energy also by this electron you are seeing here. So in due course, we find that there is an amount of energy that is required, which we are going to be calculating. There's an energy, what you call energy effective. There's an energy that you're going to be calculating to show that an atom, for it to lose an electron, it is supposed to overcome this amount of energy. So I don't know if you guys, I don't know for your syllabus, if you calculate that energy, but there's an energy, the formula is like this. The formula is energy is equals to, is it negative 13.6, which is the energy of an atom of hydrogen d'après an atom of hydrogen in the first energy state, that is n est égal à 1, and then n squared fois z effective squared. So this is z effective squared. So for the engineers, we actually calculate this. I don't know for the doctors. So there is an amount of energy, like the normal energy we calculate is this thing, this, just this. This is the energy we are going to be calculating. In a case where we are required to calculate, this is negative 13, what is this? Erase. Negative 13.6 over n squared. So n is just to represent the orbitals. That is n1. What you guys researched on last time was the quantum numbers. There's what you call angular, momentum, spin, and azimuthal, which is the angular. No, there's magnetic. I forgot magnetic. Yeah. So the n represents the nombre, the what's this? The couche. A couche is an orbital. It's an orbital. A couche, when you hear someone say a couche, it's an orbital. So this is the energy we're going to use to calculate just the electron, maybe an electron found in energy level number 3. You're going to say negative 13.6 over 6 over n, which is 3 to the power 2. Then you get your energy. Now we're calculating Z effective, ou bien l'énergie effective. Now that's the energy that is going to be effective for us to have this arrangement of this electron, for us to carry out the process of ionization. So it will be like there is an activation energy. I'll use the principle. I know, have you guys done energetics in chemistry? Like where you do exothermic, endothermic reactions? Has everyone done that before? Hmm?
Has anyone done it?
Has anyone done energetics, like where you talk about, or talk about reactions like, no, you have exothermic reactions, endothermic reactions, all those things?
Yes, we have.
Mm-hmm. So you guys understand what I say, what I mean by activation energy? You understand what I mean by activation energy?
Yes.
So it's the same thing. The energy effective, we're going to call this energy effective. So okay, it's fine. So this we're going to call energy effective. It will just differentiate it from the energy that that's what I'm talking about. Energy effective. So the energy effective is just like the activation energy. Now for us to have the arrangement of an electron, for us to have the removal of an electron, for us to have the removal of this electron, like the removal of it, you guys understand to say that when you are removing an electron from an atom, there is either energy absorption, energy emission, depending on which energy level you are starting from. So now this is from a higher energy level. We are removing an electron. So that means what? That is going to be energy emission. Tef, I'm asking, isn't it?
Yes, it is.
Yeah, it's going to be energy emission. We're removing an electron from the orbitals, so that's going to be energy emission. So we said whenever there is energy emission or there is emission, there is always going to be loss of energy in form of a photon. Now, it's the same explanation that we have here. For us to have this electron, like for us to have this electron removed from this atom, there is an energy that we are supposed to overcome. There is an energy we are supposed to overcome. Now, this energy is what we are calling Z, or l'energie effective, the energy that is effective for us to remove an electron. Now, before we remove an electron, we understand to say the nucleus will always possess an energy or a nuclear force that exists between these electrons and its respective orbitals. Because just removing an electron, like we said, removing an electron from its orbital is hard because of the same energy, the interaction that exists between the nucleus and the electrons. So even as we are going to be removing this electron, we are supposed to bear in mind that there is what you're calling a shielding effect. This is what we are now talking about. This is what we are saying, la notion d'effet d'écran. There is a shielding effect that the nucleus is going to is it going to have, that is going to possess over this electron. Is it clear? Is it clear?
Yes,
It's clear. Okay, so this is what l'energie effective is all about. Then constant d'écran, there are constants that you are supposed to, there's a table of constants that you are supposed to use for each orbital. There is a constant which you're supposed to use for each orbital. Then you are going to subtract the constant from the charge, which is the potential, or beyond the what do you call it, the mass of the nucleus. You get it? Eh? No, the Z is the charge, which is the electron beyond the proton. The Z that you're going to subtract. You're going to subtract the Z, that is the what is the proton number, or the electron number, sorry, minus the constant of the shells. There's a table. I just forgot to get the table, but let me just show you the table. So
Welcome, brother. Hey, I'm just looking for days.
Hey, 3 participants, 4 participants. Look, we are decreasing.
why are you guys decreasing? So
It's even answered.
why are you guys decreasing? No, I understand. It's early in the morning. I understand. So, like what's this? The constants that I'm talking about are these ones here. Like for each energy level, you are going to have a constant. So you're going to have, for example, you are going to have maybe a 0.8 for the is it the 2s orbital? Maybe you're going to have a 0.35 for the 2p orbital. It increases. So they're just constants that you are going to look up a table. You'll be given tables in the exam or in exercises. You'll be given tables that you're going to look up. But the Z, which is the proton number, that one you're supposed to know because you are dealing with atoms, be it potassium, magnesium, sodium, etc. So this constant, it's a constant. There are constants that can be looked up on a table, but Z is going to be found as in numero atomic, which is the atomic number, will be found on the atom. Just by looking at the atom, you know that, okay, this is the atomic number. So is it clear with the notion, the effect d'écran, where the electron, before it is removed or before the process of arrangement, there is going to be that shielding energy that the nucleus is going to possess over that electron. The there is going to be that shielding effect that the nucleus is going to have over the electron. You see, so when you want to remove an electron from the shell, from the orbitals, there is going to be that repulsion between the nucleus, or that attraction force, the attraction force between the nucleus and the electron in the outermost shell, or bien the electron in the second shell, depending on which electron you want to remove. There is going to be that energy that is going to be kind of inhibiting you from removing the electron. Now that is what we are calling the shielding effect. The shielding effect comes in because of the attraction forces that exist between the nucleus and the electron. Is it clear? Is it clear? Is it clear?
Yes.
And I'm saying for everyone, is it clear for everyone?
If you may repeat the summary again.
So, okay. So I'm saying, you see, you have an electron in the outermost shell, be it the outermost shell, be it in the second orbital, the third orbital. Now, we are saying the nucleus has a nuclear energy, or we are saying there is an energy that keeps these electrons in orbit. That's the energy we're talking about. That's energy is derived from the nucleus. So the energy from the nucleus is what gives these electrons, say, their orbit, like their orbit. So if we want to remove an electron from this orbit, now what happens? Because we are saying the nucleus has energy, or it possesses energy that gives these electrons their orbit. Because we are saying the nucleus gives these electrons their orbit, we are going to say, no, when we try to remove an electron from its orbit, when we want to remove an electron from its orbit, we are going to find that there is going to be a shielding effect. There is going to be that force, like, how can I, like, you see, when you're getting a magnet, when the North Pole and the South Pole are attracting, every time you want to remove them, there's always that attraction force that exists between the two different poles. Like when you're getting a North Pole and the South Pole, you attract them. Now, when you want to remove them, like disjoint them, you find that there is that force that brings them together. It's the same thing. Now, the force that you are overcoming, when you're removing the magnet, there is a force that you are overcoming, because the magnet north and the magnet south, when they attract, they are in unity. Like, say, the energy now is at par. Now, when you want to remove that, there is a force that you are overcoming, which is also calling the energy effective, or beyond the activation energy. There is an energy that you are overcoming. Now, that energy you are overcoming is as a result of the shielding effect that the magnets are possessing. So the shielding effect is where there is going to be a shielding from the arrangement or the removal of an electron. There is going to be shielding. There's going to be shielding that is going to happen, that will like refuse. It will not allow the removal of this electron. So now we are saying there is an energy we're going to calculate to say if this energy is going to be. So we are saying if this energy is going to be overcome by the atom, it means there is going to be a removal of an electron. Now, if the energy is less, that means that the electron will not be removed, because the activation energy is the energy that helps a reaction to take place. It's the energy that is going to help remove the electron. It is going to be our reference energy to say if the energy effective is greater than the energy, which is the energy potential of an atom. If it is greater, it means that we are going to be able to remove an electron. But if it's less, it means the shielding effect is greater than that of the activation energy. So we cannot remove an electron from the orbital. Is it clear? So now we go to diagram energetic. So now on the diagram energetic, this is where we arrange electrons in the order in which their energies increase. Like you are going to have energy level number 1, energy level number 2, number 3, number 4, number 5, number 6, number 6, number 7, 8, up until positive infinity. Now, this is where things become a little bit confusing, but it's easy. It's very, very easy. You just have to follow what I'm going to tell you. So, like I said, in the beginning of this, organic chemistry, we were explaining that they are what we were calling in Zambia. I don't know for you guys your chemistry, but we were calling the Kushes, which are the orbitals K, L, M, and N. We were calling as so on and so forth. So we're calling the orbitals K, L, M, and N. Now we are going to use the same type of representation or denoting. Is the same, but we are going to change a little bit. Now we're going to represent it in the form of sub energy levels. So I gave an assignment which was, now explain what the quantum number is, explain what the nombre azimutal is, which is the angular quantum number, then the principal quantum number as well, the magnetic and the spin. So from your research, most of you said that the principal quantum number denotes the energy levels. It just denotes the energy levels. Then the second one, which is the angular quantum number, just denotes the electron positions, in those orbitals, the electron position in the orbital. Then the magnetic quantum number just denotes or is used to quantify the dimension of the orbital, be it X, be it Y, be it Z, in space, of course. Then the last one, which is the spin, it is just there to explain what the interaction of electrons is in an atom. It is just there to explain the interaction of the electron. So the principal quantum number is represented by the letter N, the angular quantum number is represented by the letter L, and the magnetic quantum number is represented by the letter M, and the spin quantum number is represented by the letter MS to represent the nombre quantic spin. Now, the energy levels go as follows. So the Kush that you guys were learning, or we were learning in Zambia, we're calling them K, L, M, N. Get it clear? We're calling them K, L, M, N. That's what we're calling them. Now, we are saying those Kushes are going to have subshells. They are going to have subshells. Now, the subshells are these things you're seeing here. 1s, 2s, 3sp, 3p, 3d, 4s, 4p, 4d, 4f, etc. Is it clear so far? I've not started explaining about electron configuration, but is it clear with the energy diagrams? So the energy diagrams will always progress in increasing energy levels. So the lowest energy, which is negative 13.6, is for n is equals to 1. For n is equals to 1. And the highest energy is going to be at n is equals to positive infinity, which is going to give us 0. So energy will always move from negative 13.6 to positive 0. There is no positive 0, there's no negative 0, but to 0. That's the energy variation we're going to be looking at. So the lowest energy we're going to have is going to be negative 13.6, and the highest energy we're going to have is going to be 0. That is for positive infinity. And we are saying, we were calling these Kushes, that is the shells, we're denoting them as K, L, M, and N, which is here. We are saying this is going to be a K, L, M, and N. Now, we are also saying or stating to say that, okay, these are the energy levels that we have, or the Kushes. So if these are the Kushes that we are calling K, L, M, and N, we are going to also now look in detail, like what each couche has, if it has any subshell. So we are saying the first shell, which is the K, has a subshell, which is we're calling the S, 1S. And the second shell, which we are calling as L, is it KL? The second shell, which we're calling as L, has two subshells. That is the S, the 2S, and the 3P. Then the following one has a 3S, 3P, and 3D. The last one, it continues up to positive infinity. It has the 4S, 4P, 4D, and 4F. Is it clear? Is it clear?
Yes, it is.
For everyone, is it clear for everyone?
I'm not clear on. You're talking about these energy levels. Though these energy levels that you're talking about being like orbit, the subshells, the 1S, the 2S, and the 2P. So does this mean like the first one, the 1S that's there, is it closer to the nucleus? Then the other one is further until you reach 4, which is the furthest.
Exactly. That's okay. That's what I'm explaining. But let me just do this. Let me say K L M N. So this is what I mean. So here we have the nucleus. Here we have the nucleus. So this is energy level number 1, energy level number 2, energy level number 3, energy level number 4. Now we are saying in Zambia we were representing this in this way. We're saying 1. So we're going to say A, 2, 3, like that. So we're saying this is how we're arranging it in Z, which is the same thing as this. So the first energy level is what we are calling K. The second energy level is what we're calling L. The third one is what we're calling M. And the last one is what we are calling N. Now, each energy level has got what we are calling also a sub-shell, a sub-energy level, in other words, a sub-energy level. Now, the sub-energy levels are defined in form of the quantum numbers. That is the angular quantum number, the principal quantum number, and the magnetic quantum number. The spin is not a problem. The spin part is not a problem. But it is defined in these three. It is defined in these three: the angular quantum number, the principal quantum number, and the magnetic quantum number. So the numbers you're seeing here in front, that is 1, 2, 3, 4. They are just representing these energy levels as you increase, as you progress in the number of periods. Because we said in the periodic trends, we're going to look at the periodic table, but not in detail. We said the orbitals also help us denote or explain which energy levels, like how many energy levels that an atom has. So when you count here and say you have 1, 2, 3, 4, you'll find out that this atom is found in period 4. An example of an atom found in period 4 is I think that's calcium. Calcium should be found in period 4. It has 20 electrons. So when you do the electron configuration, the normal electron configuration you're doing in Zambia, the normal electron configuration, which is 2, 8, 8, 2, it's going to show you that the atom calcium is found in period 4, and the period 4 you got it from the energy levels. You can just look at the energy levels, say, okay, this is 1, this is 2, this is 3, this is 4. It's the same principle. Now we are going to just denote these energy levels in subshells. We're going to represent it in a form of subshells. That is, we're going to have the 2S, P, 3S, 3P, 3D, 4S, 4P, 4D, 4F. Now, is it clear, Mutale, on this part? On this part where we're just denoting the energy levels in form of subshells. Is it clear?
Yes, it's clear. Thank
Okay.
you.
So now we're saying because we are explaining them or denoting them in form of the 3 quantum numbers, that is the principal quantum number, the angular quantum number, and the magnetic quantum number, we are also going to denote these energy levels with the number of electrons that each occupies. So in the assignment I gave, I said, now, how many electrons maximum does the s orbital occupy? How many electrons does the p orbital occupy? How many electrons does the d orbital occupy? And how many does the f orbital occupy? So you're going to give me a number of electrons that each occupy. How many electrons does the s occupy? How many electrons does the s orbital occupy? Hmm?
2.
It occupies 2 electrons. How many electrons does the p orbital occupy? The p.
6.
6. So how many electrons does the d orbital occupy?
10.
And the last one, the f?
14.
Exactly. So if you've noticed, it's a progression of 4, 4, 4. So the first one occupies is it 2? Second one occupies 6. The third one occupies 10. The last one occupies 14. So it's the same. It's the same notion we are going to use. That is the same thing that we were learning in Zambia. Say the first two occupies 2. The third one occupies 8. The third one occupies 8, and the last one occupies 18 as you continue. But it's the same notion we're going to use. We are going to use the notion that an electron that is occupied by the s orbital will go as far as 2. That for the second one, which is the p orbital, we are going to go as far as 6. For the d orbital, as far as 10, and for the f orbital, we are going to go as far as 14. We are not going to surpass these numbers, because if we surpass them, it means we have not obeyed the number of electrons that each orbital occupies. Is it clear?
Yes.
Okay. So, no, I'm saying for everyone. Is it clear for everyone?
Yes, it's clear.
Okay. Then, before we even go to electron configuration, there is a, okay, let me do electron configuration, then come to regulate show. It's like you guys, you might gonna maningai.
We might touch it disturb my Nigerian, so I'm gonna check it.
Nigerians disturb you.
Yes, they make a lot of
It's
noise.
10 o'clock.
Yeah, I knew it that network yavuta.
Vuta kuno.
What's happening? Now the problem is I can't have a class usiku. The problem that time you're supposed to be doing something else, you guys. Unless if you want to have a class usiku. So I'll take, how many are you guys? You guys are 4. I want each one of you to give me an atom from number 1 to number 20. Number 1 to number 20. First.
Potassium.
Huh? What was that?
Downga.
At what?
Potassium.
Okay, potassium. Here, next one.
Calcium.
Next one. Next one. I said top 20.
Nitrogen. Sulfur.
Okay.
Copper.
I said top 20 bosses. So I also give myself 1 so that we finish this part. So I'll give myself a simple one, that is say, okay, give me a simple one that is on is it top 10? Give me a very simple one on top 10.
Lithium.
Okay, lithium.
Beryllium.
Okay, lithium is better because, okay, beryllium and lithium are neighbors, so we can use both. How do you spell beryllium? Beryl. How do you spell it? Like this. Is it that how you spell beryllium? So, please guys, follow me slowly but sure. Slowly but sure. So when we are doing the electron configuration, we are going to apply what we are calling règle de construction. In English, it's called the Aufbau's principle. It also in and then the German is called Kleschowski. It's called something like that. Now, it's the same principle we're going to use when doing our electron configuration wherever you go. If the electron configuration is to deal with the subshells, it's the same one we're going to use. It's the same one we are going to use. Now, I want you to follow me. We know, slowly but sure. Slowly but sure. Now, I want you to picture the periodic table. As I'm going to be explaining this, I want you to picture the periodic table in this way. How am I going to write it for you guys? Let me write the periodic table just a bit for you. So the periodic table is like this. So 1, 2, 3, 4. 1, 2, 3, 4. So I'm going to have like So do you guys know the periodic table?
No, I don't even remember.
So this is 1, 2, 3, 4, 5, 6, 7. Space, Add 1 here. So I'll give, so hydrogen, there's hydrogen there. No, our periodic tables are done to scale. There's hydrogen there. We'll do this. So there's hydrogen. Hydrogen, sorry. Then what follows hydrogen? What am I periodic table? There's helium there. Then there is what follows helium? Lithium. There's lithium. Then there's beryllium. Then there's what?
Boron.
There's boron. After boron, you have carbon. You have nitrogen. You have oxygen. You have fluorine. You have neon. Then you have sodium. Then you have what do you have here? Magnesium. Then you have what here? After magnesium, aluminium. After aluminium, you have silicon. Silicon, you have what after silicon? Phosphorus,
Phosphorus.
sulfur. After sulfur, you have what? Chlorine. After chlorine, you have argon. Tefio. Then we come to the potassium and the calcium. Now, I want to put this other one up so that we have scandium there. So now, I want you to picture this periodic table as we're going to be doing the electron configurations. You picture this periodic table as we do the electron configurations. So what you can also use as reference.
Alert from iCloud storage is almost full.
So what you're supposed to picture, is this here, group 1 and group 2 is called, group 1 and group 2, they are called S blocks. They are called S block. That is group 1 and group 2. They are called S. Then the transition metals here are called the D block. Then these ones here, the lanthanides and lanthanides, these ones here, they are called F block. Then the last one, which is going to be, what do you call these ones? They're called the P block. They are called the P block. So even as we are going to be filling in the electron, I'll show you two methods. I'll show you the two methods you're going to use. The first one is where you just use, the first one is where you just use, what do you call it? You will just use, you just use the periodic table. And the second one is where you use the principle of how many electrons are occupied by this orbital, how many electrons are occupied by this shell. That's the other method you are going to use. So now how am I going to? Okay, so we are saying we are arranging these orbitals in increasing quantum numbers. We are arranging them in increasing quantum numbers, 1s, 2s, 3s, 4s, into the suite. But we are also supposed to consider which orbital is occupied by which electron before we go to the other. So, d'après Affenbaugh's principle, ou bien la règle de construction, ou bien la règle de Kleshowski, it states that you're going to have the first shell, which is the one that has a energy level number 1. So quantum number here, the principal quantum number is 1, and the shell is what we're calling the S. Now the second one will be the 2, like it's just numbers like 1, 2, 3, 4 up to infinite. But what will be changing will be the number of shells. We're going to have the 2s and 2p. So in the second shell, we have two orbitals. That is the S and the P. We have the S and the P. I'll show you when it comes. I'll show you how it comes about when we look at the periodic table method. Then the third one, we have 3s, 3p, like that. 3p, like that. Is it clear? Is it clear? That's how you're going to be moving. So you have, first, you're going to start with the 1s. The second would be 2s, 2p. This is for the second shell. Then the third one would be 3s, 3p, which would be for the third shell. So this is the first shell, second shell, and third shell. And what do you call it? Third shell. Is it clear for the first three shells? Is it clear for the first three shells? Is it clear for the first three shells?
Yes, it is.
For everyone. When I say is it clear, I mean everyone. Is it clear for the first three shells for everyone?
The lesson does repeat itself.
So what I'm saying is the energy levels that we looked at, were in form of, is it K, L, let me use capital letters, L, M, like that. So we're saying the first energy level is called K, the second one is called L, and the third one is called M. Now, the order in which we are going to use this règle de Kleshowski, which is la règle de construction, how we're going to be constructing our electron configurations, we are going to use this principle. That is, when we are starting to fill in the energy levels, we're going to start with the one with the least energy, that is one with 1s, that is the lowest energy is n is equals to 1. So this can also be called n est égal à 1, n est égal à 2, n est égal à 3. Ou bien vous pouvez l'appeler K, L, M. You can call them K, L, M. You can also call them n is equals to 1, n is equals to 2, n is equals to 3, because it also denotes the energy levels. Don't forget the three quantum numbers, please. The angular, the magnetic, and the principal quantum number. These are very important. So we are saying, when we start filling in the energy shells, the first one will be 1s, the second one will be 2s, 2p. So it means that the L orbital is made up of two shells, that is the 2s and the 2p. Now the third one is also made up of two shells, two. That's the 3s and the 3p. That's the 3s and the 3p. Now when you come to the fourth one, this is where I'll add in one or two things. But is it clear for the first three? The first one, which is energy level number 1, also known as K, is just going to have one shell. That is 1s. The second energy level will have two shells. That is, we are calling the second energy level to be L. It will have two. It will have the S and the P. Now we're saying 2 is the quantum number, or 2, is the one that denotes the energy level. It will have two energy levels. That is the P and the S. Now the third one is going to have also the P and the S. Please take note. We are not saying it's going to have two because it's not going to have two energy levels because there's a 2 here. No. We are not saying there are 2 here because of the energy levels here, no S, P at there 2. No. It is because the quantum number, which is the principal quantum number 2, only has two shells. It only has two shells. If it had 3, would have gone as far as writing 2, for example, say X. If it had 4, would have gone as far as writing 2, X, Y, etc. But the maximum that the second shell has, it can only go as far as 2. Same applies to the third one. It only has 2 energy shells, but the principal quantum number is 3. So is it clear for the first 3? Just for the first 3. For the first 3, is it clear?
Yes, it is.
Okay. So now we are saying our example is lithium. I'll start with lithium. So if we were to configure lithium has an atomic number of how many? Lithium 3. So that means if we want to occupy the electrons, that is, we want to have the electrons occupied. I'll use this method. If we want to occupy each orbital with the electrons that each shell has, like it can occupy maximum. So we have 3. Now, what we used to do in Zambia was we used to write this electron configuration as 2, 1. This is what we used to do. Take this configuration as 2, 1, isn't it, for lithium?
Yes,
It was 2, 1. It was 2, 1. The same thing is what we are going to do here. The same thing is what we are going to do. So we are saying the highest number of electrons that the s orbit can occupy is how many? The s orbit, how many can it occupy? The s, how many can it occupy? Maximum
2.
occupies 2. Then the s orbit, how many can it occupy? Maximum again. Maximum, how many does the s orbit occupy? Maximum
2.
exactly, it's 2. Now in this case we only have 3 electrons. We only have 3 electrons, and we've already occupied the 2 here. So how many are remaining?
1.
There's only 1 electron remaining. So therefore the electron configuration for lithium will be 1s. Now these s's, these numbers are supposed to be raised there. Like you're supposed to raise them to my powers, like the power 2, like that. This one here also to the power 1, like that. Now because we have no electron to occupy the 2p, we forget about it. Therefore the electron configuration for lithium becomes 1s to the power 2, 2s to the power 1, 1s to the power 2, 2s to the power 1. So now I'll use the periodic table method. So the periodic table method goes like this. So we are saying, please, Panono, get what I'm saying. Do small. Where you don't understand, you tell me so that we repeat. Where you don't understand, you tell me so that I repeat. So we are saying this is the first energy level. It's called 1 TeF. It's called energy level number 1. Also, yeah, it can be called period number 1 or energy level number 1. This is period 1, energy level number 1, period 2, period 3, and period 4. Now, when you're filling in or when you're doing the configuration, you can use a periodic table, but it's going to be taking time for you. You go to the periodic table and do it. So you'll be doing this. Say, this is the s orbit. This is the s orbit. This is the s orbit. Yeah. Don't worry, I'll explain why. What's happening? So the idea is when we're using the periodic table, we are going to use just for the references of this just for reference for this type of configuration, we are going to move helium from the P to the S. We are going to move helium from the P to the S. We are going to see how the configuration for helium comes in, how okay, maybe let me say why we are saying we have to move it from the last layer, from the P, and move it to the S. So the idea is, we know that helium is a transition, or is a noble gas, and all noble gases obey the octet rule. The octet rule, which is all electron shells, that is, all shells are occupied by the maximum number of electrons. Maximum number of electrons. So if we were to give the electron configuration for what's this? What do you call it? For helium, it would be, so I'll create another page. For helium is a number what? Atomic number. Helium, atomic
2.
number 2. So if we're to give the electron configuration for helium, that is 1s, 2s. So just as far as I just want to, maybe even 2s, 2p, like that. So we're saying how many electrons are occupied by the s orbital?
2.
2 electrons. So there are 2 electrons occupied by the s orbital. Now, how many electrons are occupied by the 2s? Like in the case of helium, there's nothing, isn't it?
Yes.
And same applies to 2p, isn't it?
Yes.
Therefore, this becomes a configuration for helium, isn't it?
Yes.
Which means it has obeyed the octet rule. The octet rule states that the maximum number of electrons that each shell is supposed to occupy, that's the octet rule. The the orbitals are supposed to occupy the maximum number of electrons, the maximum. If a shell occupies 20, it's supposed to occupy 20. That's the maximum. So it is found that helium respects the octet rule, which states that it is supposed to occupy the highest number of electrons, that is in the case of an atom. Now, it is found that on the periodic table, all noble gases occupy the highest number of electrons or the maximum number of electrons. So it is for this reason why I moved helium from P to S. Now, this is how the configuration for the periodic table comes in. So we're still on the lithium example. I'm still on the lithium example. So we're saying, let's hope everyone is here. Now, Kondon is not here. Okay. Anyway, I'll still explain it. So we are saying this is period 1. This is period 1. This is period number 1. E. This is period number 1. This is period number 2. Period number 3. Period number 4. Top 20. Not push. So what you do is you come here. Lithium is number 1, 2, 3. Lithium is number 1, 2 is number 3. So what you do is you come here and say, okay, for us to reach where lithium is, we are supposed to go in for us to reach where lithium is, we're supposed to take like 3 steps. We are supposed to take like 3 steps. That is 1, 2, 3. This is where lithium is. We're supposed to take like 3 steps. This is what you do. So you say, okay, we know that the first period number 1 here, number 1, and this here we called the S block. We called this group 1 and group 2 the S block. We called group 1 and group 2 the S block. So now for us to reach where lithium is, we are still in the S block. We are still in the S block. There's nothing on the P. We are still in the S block. And we're saying this is period 1 and this is period 2. So we're going to say, okay, lithium is found in period 1, that is, and there is also a period 2. So for us to reach where lithium is, there is period 1 and period 2. This is period 1 for helium and hydrogen, and period 2 for lithium. For us to reach where lithium is, for us to reach, like there's a steps, just like steps, like 1, 2, 3, like you're moving from one place to the other. So for us to get to lithium, we're supposed to pass through hydrogen, helium, then lithium. So we are saying lithium is found in period 2. Now for us to get to lithium, we're supposed to go through hydrogen and helium, then go to lithium. And we're also saying that this is found in period 1. This is found in period 1, and this is period 2. This is period 2. So, and we are also calling this here, that is group 1 and group 2, as the S block. We are calling it the S block. Therefore, the movement or the trajectory we are going to take will be 1S, that is 1S, then go to 2S, 1S and 2S, 1S, then 2S. Then how many electrons are going to be occupied by the 1S? We're going to count, that is 1 and 2. That is 1 and 2. So we're going to have a 2 there. What have I done? So 1 is like that. So for us to move from hydrogen to helium, then to lithium, the trajectory is we're in the first orbital, that is the first period, and we're in the S block. So that is going to be called 1S. Now, how many electrons does 1S occupy? Not even using that rule. No, it occupies 2 maximum. Just counting. Say for us to get where lithium is, we're going to take how many steps? We're going to first step 1, second step 2. So you come here and say 1, 2, that, so 2. Now, for us to get where lithium is, how many steps are we supposed to take? We are in period 2, and we are in the S block, which is also the second shell. Now, for us to reach where lithium is, how many steps are we supposed to take? For us to reach where lithium is, it's one step, isn't it? It's just one step. It's just one step. So the electron configuration now will be written like this. To be 1s2, 2s1. Is it clear with a periodic table method? I know it's a bit confusing, but I'll use another method. I use another what's this element. Is it clear so far with both methods? The first one where we use the number of electrons that each shell occupies, and the second one is where we just count steps and which period it is found in. Is it clear for the first two?
For the one where we just count is clear, but the periodic table, I'm lost.
Okay, so I'll do this. I'll use fluorine. I'll use fluorine as an example. So fluorine is a number 9. So please follow me. We know when. So 2. Okay. So say 2s. Let me just do this, maybe to make more sense if I do this. So fluorine is here. Fluorine is at this position. Fluorine is at this position. Now, it is found at the P block. P block. It's found at the P block. That is where the nonmetals and all these metalloids are found in. That's the P block. Now, with the periodic table method, I said we are going to consider how many steps we are going to take for us to reach where lithium or fluorine is. So this is how we do it. Follow me. So we have helium and hydrogen that are at the S block and are in the first period. So in the first period, we are going to have 1s. So in other words, these blocks that you're seeing, the S, the P, and they at some point, we're going to see that they also denote the energy levels. So here, the first one here is helium and hydrogen. Now, they are found in the first shell. Now, the question is, we want to get to where fluorine is. How many steps are we going to take? So the first step will be, because we're in the first period, and that is called the S block, or be in the S orbit, the first period, and it's called the S orbit. That is 1s, like that. I'll come to the electrons later. Then we are now moved to the second period. Fluorine is found in the second period. We are moved to the second period. Now in the second period, we have 2. This is period number 2. We have period number 2. This is period number 2. So we come to period number 2, like that. Then, before we even forget about period number 2 from the S, we also have period number 2 on the P. We have period number 2 on the P. Now, period number 2 on the P. So, period number 2 goes like that, goes to the P as well. So, you have something like 2P, like that. Is it clear? Upper pen, is it clear?
Yes, it's
For everyone.
It's clear.
Okay. So now the electrons, now how we occupy the electrons. So we are saying we just count. With a periodic table, you don't have to even master how many electrons are occupied by the shiny, how many electrons are occupied. You just count. So we're saying in period 1, we are on period 1. We are in period 1. Period 1, how many are there? And how many atoms are there? We just count, say 1, 2, and they are in the 1s. So you come here and say there are 2. I'll use red. And say there are 2. You counted just 2. They are helium. There's just helium and nitrogen or hydrogen, they're just 2 in period 1. This is 1s. They're just 2. 1, 2. They're just 2. So you come here and say 2. You go to the next one, which is the s, which is the 2s. Sorry, which is the 2s. You also count foot. How many are there? There's 1, 2. You come here and put your 2. Now to the last one. You also count the same thing, just counting. You just count 1, 2, 3, 4, 5. Then you come here and say 5. Is it clear? I'll use another example so that maybe it makes more sense. So fluorine, I'll use another one in the period 3. I'll use sodium. So I just make it a bit. So sodium. So sodium is found in this is number 11. So we are using the periodic table method, because I'm pretty sure you guys with the ones where you how many electrons, that one is a bit easy. The other one is a bit okay. It's easy also. Both methods are easy. Let me explain. Sorry. So we are in period 1, and this is the S block. So this is period 1, and this is the S block. So it's going to be 1s. 1s. Then we go to period 2. We have 2s, that is the 2 that is for the period, and the s for the orbital or for the block. Then we are still in period 2. We don't just have, because for the first one we only have one orbital, that is the s. We do not have the p this side for helium. So the reason why I moved helium from this p to the s is to satisfy the octet rule. Now in period 2 we find that there is a 1s. So in period 2 we have 2s. Then on the other side, still in period 2, we have the 2p. In the same period, that is the 2, we have the 2s, and we also have the 2p. The 2p. Then sodium is found in period number 3. It's found in period number 3, but we are still in the s block or s orbital. So we are going to have 3s. We are going to have 3s, which we are going to. So we're going 3p and 3s like that. So now, how do you come up with the electron configuration d'après la periodic table? So you just count, like I was saying, just count. So you count. Our target is sodium. Our target is sodium. So you just count. Say 1, 2. That is for the first shell. For the first shell, that is 1s. For the first shell, 1s. You're going to count. How many is it? 1, 2. You come here and say, okay, there are 2 electrons. You come to the next one. Because takuli for the p, there is nothing for the p. So it's automatically that you're going to start again on the second orbital. So for the second orbital, you still count. Say 1, 2. You come here and say there are 2 electrons. Then you go to the other side of the p for the second period. You count to say 1, 2, 3, 4, 5, 6. There are 6. There are 6. And where is our sodium? At position number 3. That is for the 3s. And number 1. Is it clear? But please take note, these 2 numbers, they're supposed to be raised like that. Is it clear for the periodic table method?
I think with more examples, when I try to do them on my own, maybe I can actually get, because the general idea. That's night. Quite no certified. We know the best night.
No. I'll do the periodic table method with all the examples that we have. But is it clear? Is it making sense for some of you? Is it making sense? Where they just count? Is it making sense?
Yeah, I understand.
Okay. So now we go to potassium. That was Taonga's example. So potassium is number 19. So we are going to go with the first method that Mutale is comfortable with. So the first one. So the configuration for potassium in Zambia, we say 2,8, 8, 8, 1. This is the configuration that we learned in Zambia. You.
Yes.
So we understand that this potassium is found in period number 1, 2, 3, 4. So we have 1s, that is for period number 1. 1s, that's for period number 1. Number 2, we have the 2, we have the s and the p. We have the s and the p. Same applies for the third period. We have the s and the p as well. Then for the third period, we have the s, but when we continue, we find that there will be d and all those things. So for the third period, we will have another s. So it's s, p, s, d, then p, but s depends on for now we'll just mean per s. For now we'll just go as far as the s. So period number 1, period number 2, period number 3, period number 4. So 2s, 2p, 3s, 3p, tefyu. Nakupwa tefyu. Nakupwa. No, you guys not following. There are 1, 2, 3, 4 energy levels. And this is just 1, 2, 3. As in, these things you're seeing here, like this. It does not show that this is it doesn't show that just the 2s 2p is just one shell. No, the 2s 2p is one orbital. The 2s 2p is one orbital. Same applies to the 3s 3p. Those are single orbit. Like it was. Let me. Okay, I'll maybe it will make more sense if I do this. 4s 4. Okay, there's no 4p, but there will be 3d. But I just want to make a point here that maybe you guys make a little bit is a panko sense. Is a panko sense. So what it is that this energy level we are seeing here, the 2p2s, is what we were calling our L. The 3s 3p is what we were calling our M. And the last one, which is 4s, this is what we're going to be calling our N. This is what we're calling our N. I didn't put the N here. But this is what we're going to call our N. That is 4s, 4p. This is what we're going to call. Okay, could be 4pi, but 4p comes in later on. But for now, there are exceptions to this rule. We are going to call this our N. So these energy levels, these are 1, 2, 3, 4. You don't count them independently like 1, 2, 3, 4, 5. No, you count this as 1, you count this as 2, you count this as 3, you count this as 4. Is it clear? Then to maybe just solidify on another thing, the configuration electronic for fluorine in Zambia was written as 2,8,1 tefyu. Sodium was written as 2,8,1. How many was it? Comma what? Comma 8, that's going to give 10. Comma 7. And these are the electron configurations that we did in Zambia. Like these are the standard electron configurations we did in Zambia.
Yes.
Like, is everyone clear with this one, the 2,7 for fluorine and the 2,8 for sodium? Is it clear, Yakuzed configuration?
Yeah, but easy.
Okay. So what it is that it's the same thing we're doing, you guys. There's nothing complicated. You see, I'm saying this here is an orbital. And this here is also an orbital. It's also an orbital. When you add the 2, when you add 2 and 5, how many do you get? How many do you get when you add 2 and 5? How many do you get? How many do you get?
7, boss.
7.
Exactly. This is the same as 2,7. It's the same as 2,7, the electron configuration that you guys did, because it's the same. It's the same. Take 2,7 when you add the 2, because we are saying the 2s2 and the 2p5, it's just one orbital, which we are calling the L orbital. It's the same. C'est la même chose. It's the same orbital. C'est la même chose. Now, it's just that we are now considering the sub-energy levels, So we have the 2s2 and the 2p5. This here is the same as 2,7. It's the same as 2,7. But now we are just denoting it in the form of sub-energy levels. So the first one occupies 2 electrons. The second one occupies 7. Now the 7 is divided by 2. Now there's the s orbital and the p orbital. Now the s occupies 2 maximum. The p occupies 6 maximum. But now we do not have 6 electrons for the fluorine atom. We only have as far as 5. So it's going to occupy 5. And therefore, the electron configuration will be 1s2, 2s2, 2p5, which is the same as, maybe I put an equal sign here, right? Which is the same as the Zambian one that you guys have learned from, I don't know if it's grade 12, which is the same as this here. Is it clear? Then for sodium, c'est la même chose. For sodium, same. We said sodium's electron configuration is 2,8, 2,8, 1. Te your electron configuration ya ZD. Te
Nini?
It's the same one, 2,8, 1, which is the same as if we were to add these two. How many? I'm not saying every time you are supposed to add. I'm just showing you where it's coming from, like the background. You shouldn't be confused because these things should be the same. Is it clear? Like you can see where the 2 is coming from. But no, the 2 you can't see it here. I'll use yellow food. So is it making any sense that the 1s2 is what we were saying 2? The 2s2p is what we were calling the 8, and the last one, the 3s1, is what we were calling the 1. Is it making any sense, somebody?
Yes, somewhere it's making sense.
As in, is it making somehow?
No, I get it. I get what you mean. I
No,
get
as
the
in, is it,
explanation
no,
that
I'm
you
saying not only you, Mkali, for everyone. I'm saying everyone. Is it making any sense? Is it making any sense? Is it?
Sense. Yes, yes.
No, I'm saying for everyone. How many?
Agreed.
Is it Taonga? Is it making any sense?
Yes, it's making sense.
Very much sense. So if I was to give you an atom here, you would configure.
Yeah, we'll try to.
Kennedy. Is it making sense?
Yes, yes.
Mutal, is it
Making
making sense? Is it making sense?
Yes, it is.
Okay. So it's the same as the Zambian one, but don't, in your exams when you go to faculty, don't use 2,8, 1. It's wrong. You can use 2,8, 1 to just justify, maybe just say, okay, maybe what I've done is correct. Yeah, but it's always going to work out like that. So we were in the potassium example. So these energy levels, these 2,8, 1 can guide you also. You can say, okay, no, this one is supposed to have, how many? It's supposed to have 4. The first one here, 1. What color are we going to use? We use this one. The first one, 1. The second one, the third one, and the last one here. That's how it's supposed to be. That's how it's supposed to be. Then you just put in now the number of electrons. You put into my number of electrons. So we go with the periodic. No, we'll go with the first method, where we just count how many number of electrons that each shell is supposed to occupy. Okay. Now, how many electrons maximum for the s orbital? Maximum for the s orbital. Check first, guys.
Two.
How many? Two.
Two.
For the s
Two.
encore. Okay. 2. For the p encore.
6.
Huh? For the s encore.
2.
For the p encore.
6.
For the 4 encore.
2.
1.
Oh,
It's
I
going to
mean
be
1.
It's going to be 1. So now, in other words, the 2,8,8,1 is what you're seeing here. The 2,8,8,1 is what you are seeing here. So now, is it clear as in for everyone? Is it clear for everyone? Or I repeat, is it clear for everyone how we came up with 1s2, 2s2, 2p6, 3s 2, 3p6, 4s1. Is it clear for everyone? Or I repeat how we came up with this configuration?
It's clear.
It's clear for everyone. Mr. Kenneth, is it
clear.
clear? It's clear, Mr. Kenneth.
Yes, sir.
Dawanga, is it clear?
Yes, it is.
Alhamdulillah. Now for the periodic table, maybe for the periodic table it will even make more sense now. So we're saying 1. Mutala, I know it's clear. 1 is
Yes.
so 2s, 2p, 3s, 3p, 4s. Please, another thing, when you have been given a question, these are just my simple tricks. When you have been given a question, even put to kuntanshu, even put potassium, say potassium, maybe say atomic number 19, configuration électronique est égale à ça. You put a chemical formula, oh no, not chemical formula, symbol. You put also say no, potassium is equals to, that is number of electrons, that is 19. It is equals to same thing. So with the periodic table method now we count. The periodic table is just counting. Just counting. Potassium here, but if potassium is here, potassium. We're just going to count. So our target is potassium. We are going to count. This is the first period, the second period, the third period, and the fourth period. Now, this is the same thing as what I was saying here. This is the first period, the second period, the third period, and the last period, which is the fourth period. C'est la même chose. It's just that the periods now have got sub-energy levels. So we are going to count. How many are here? You're going to count it 1, 2 for the first energy level, or for the first energy level. Of course, the S, there are only 2. You counted how many? 1, 2. Now with this method, you don't have to memorize how many electrons each shell is supposed to occupy. No, it's just counting. You just count, say 1, 2. You come here and say you have 2. You are in the second energy level. You are in the second energy level. You just count on call. So you're counting how many? 1, 2. There's nothing for the S sniper part. There's nothing more. S sniper. You come here and say there are 2 on call. We are still in the period number 2. We are still in period number 2. We have the S. We are done with the S. And there's also P. There is also P. How many do we have? We are going to count and say 1, 2, 3, 4, 5, 6. We're counting atoms. We're counting atoms. Not just none. I'm just counting to my boxes. No, I'm counting atoms. There's boron, there's carbon, there's nitrogen, there's oxygen, there's fluorine, there's neon. I'm counting 1, 2, 3, 4, 5, 6. Yeah, 6. Naipwa P. Not push a P. You see? 6. We are in number 3 now. This is period number 3. Period number 3 also has a S and P. It has S and P. So we're going to count how many are there for the S. We have 1, 2. So 2. forge ahead for the other part, that is for the 3p. We have how many? We have 1, that's aluminium, 2 silicon, 3 phosphorus, 4 sulfur, 5 chlorine, and 6 argon. So we are going to have 6 here. And for the last one, potassium is at period number 3 or period number 4, and it's number 1. It's just 1. This is where we are supposed to reach. This is just 1, so we're going to have 1. Therefore, the configuration electronic becomes this. Is it making sense now? With this one,
Yeah.
with this one, you don't have to master how many electrons are occupied by which energy level. No, you just count. For us to get to where lithium is, how many movements am I supposed to make? But you're supposed to take into consideration. You're supposed to take into consideration the what? You're also supposed to take into consideration which energy level you are in, or which orbital you are in. No, I'm saying, is it clear for everyone? For everyone.
Yes, it's clear.
The periodic table and the, what do you call it? The other method.
Yes, it is.
Okay. So now,
Yeah.
okay. So now we do the last few examples. Then I bring in another notion. So calcium is number 20. Number 20. And the configuration electronic is 2,8,8,1. 2, sorry. So with the, what do you call it? I'll call it the Mutale method. The Mutale method is 2s, 2p, 3s. Please take note, there are how many? There are 1, 2, 3, 4. So 3p, we're going to have 4s. Now, quantitative 1, 2, 3. Oh, yeah, this is 1, 2, 3, and 4. Like that. 1 is there. Second one is there. Is it clear? The first 4 orbitals. The first 4 orbitals. The first 4 orbitals. Is it clear with the Mutale method?
Yes.
So now, how many electrons are supposed to be occupied by the s orbital maximum? TNI.
2,
Encore.
2,
The P,
6,
the S,
2,
the P,
the 6,
and the S.
2.
So now you want to take.
Yeah.
So not forgetting that you're supposed to raise these numbers to my powers. Raise it to the power. So raise this one to the power. This one power. This here power. That power. This to another power. Then, like I said, you even add calcium, casimbo. Say number 20 has this configuration electronique. So this is called the configuration electronique. Now with a periodic table method, number 20 So I'll be counting just now. So this is where calcium is. Calcium is at this position. So we are supposed to count all the way to calcium. So period 1, period 2, period 3, period 4, which satisfies our I don't know if it's a formula or generality here. So we are going to start counting. So in period number 1, that is for the S, we have how many? Helium and hydrogen and helium. So that's 1, 2, 1, 2. This is our 2 here. For we don't have the P. We don't have the P for the first period. We don't have the P for the first period. Now we go to the second one. We go to the second one, which is lithium and beryllium. How many do we have? We only have lithium and beryllium. They are 1, 2. That is 2s2. Then we go to the third one. Oh, sorry, the second one still. We have how many? We have boron, carbon, nitrogen, oxygen, fluorine, and neon. That is 1, 2, 3, 4, 5, 6. And we're going to have the 6 here for the 2s. 6 for the 2s. What's happening? 6 for the 2s, like that. Then for we're still targeting calcium. We are still targeting calcium. So we have 1, 2 for period number 3. That is in the S shell. We're going to have 1, 2. That's magnesium and sodium. That's 2 that we are seeing here. That's the 2 we are seeing there. Then on the other end, we have still in period number 3. We have aluminium, silicon, phosphorus, sulfur, chlorine, and argon. That is 1, 2, 3, 4, 5, 6. Still have 6 electrons. That is for the 3p, 6 electrons. Then the last one is 1, 2. That is for period number 4 in the S block, S orbital. That is 1, 2. Then this is our 2 there. Now I think it's making sense, the periodic table method.
Yeah, it makes sense.
It makes sense now, eh?
Yeah, sense na idea of what.
Yeah. So yeah, the one for swattering is not even for, you've not even swatted. It's just how many electrons occupy, and you look at how many you have. So the configuration that we're doing in Zambia, which is 2,8, 2,8,
It's 11 o'clock.
2. Sorry. This is what you're seeing here. 2,8, 2. Now what I'm trying to say is this you're seeing here, the 1s, this is what you call the SPDF electron configuration. What you're seeing here, Sela Mem shows it's nothing different from this, the 2,8, 2. Sela Mem shows it's just that this one is showing the sub energy levels, like how electrons are bonded, like how electrons are arranged in these orbitals. How electrons are arranged in these orbitals. Same applies to this one. C'est la même chose avec 2, 8, 8, 2. It's the same. It doesn't change. It's the same. Even as you go on, you find that there may be a number of electrons that are going to be added, but it's still going to maintain with the Zambian method, if I call it that. It's still going to maintain with the Zambian method. Then the last one, which is nitrogen, 7. That's 2, what? 2, what? 2, 5. 2,5. Then, so you say nitrogen, like I said, you say maybe 7, that is the atomic number, will be equals to, so the Mutale method, 1s, 2s, and 2p. So how many electrons are occupied by the first orbital? That's the s. 2. Second one?
2.
And the last one?
3.
1. 3.
Why 1? Okay, now yes.
Yeah, so that is it. So this is now the 2,5 that we learned, because dying. 2,5. 2,5. Now, with the periodic table method, so with the periodic table method, we are counting, say nitrogen is there. So period number 1, we have S, that is 1, 2. This is the 2 here for the first period, and for the S shell. For the S shell, we have 1, 2. We don't have the P for the first shell. We don't have a P for the first shell. Then the second one is that's the second orbital. We have 2. We have the P and the S. So the first part is going to be the S. That is 1, 2. That is lithium and beryllium. This is the 2 you're seeing here. 2. Then the other end, we have boron, carbon, and nitrogen. That is 1, 2, 3. That is the 3 you are seeing, which also justifies the 2,7 electron configuration that we learned from Zambia. Is it clear with all the examples that we have done so far?
Yes, boss, it's clear.
Okay. Now, I just want to introduce one notion, just one simple notion. This notion, you apply it on all the atoms, on all the atoms. So there's also what you call the noble gas electron configuration. Have you heard anything about that? Noble gas electron configuration. Noble gas electron configuration. Have you heard it before?
I've never heard it.
Okay. Then another thing, before we come to the noble gas configuration, if a question comes and the question says, we are going to answer this question for all of the examples. If a question comes and says, what is the valency electron? Or maybe say, what is the valency shell? The valency shell. So for this one, what is going to be the valency shell? This one here, for fluorine. This is fluorine. This is fluorine. What is the valency shell going to be? Fluorine. Fluorine. Sodium. What is the valency shell for fluorine? So this is fluorine 9. Fluorine, sodium 11. So what is the valency shell? So valency. Couche de valence, c'est la même chose. Eh? That is for fluorine. And guys, same thing question guys, so that for sodium. What is the couche de valence for fluorine? And what is the couche de valence for
Isn't it the 2S and the 2P?
No. Auntie?
Isn't it like the last shell that was there?
Which is
For fluorine, wasn't it like 2P or 2S, 2P?
just a second. And please, I hope you guys also know the names of these elements in French. Fluorine is called azote. Potassium is called potassium. Calcium is called calcium. Fluorine is called fluor. Then sodium is called sodium. So you also have to know like their names on the periodic table, what they're named, all those things. So what is the couche de valence for fluorine? Couche de valence for fluorine. What is a valency shell? What do you call a valency shell? Okay, what do you call what is a valency? Maybe in other words, what's a valency? If I start from that side, what's a valency?
A shell is a shell that loses or gains an electron.
The valence is what?
A valence shell
Mhm.
is one that loses or gains an electron.
So the valence shell is the shell in which you find an electron that can either be lost or can either allow occupation of other electrons. You get it? Yeah? So a valence shell is one that can either allow the occupation of other electrons, that is what we are calling the gaining of electrons, or it can allow the loss of an electron, that is what we're calling the losing of an electron. And all those things now are what bring up ions and etc. We're going to look at that at 14 to, is it 17 to 18? So we're going to look at that later on. But now for today, just on this part, the couche de valence is the one that we are going to consider when the atom is in its neutral state. And if it's going to allow electrons, we are going to call it an ion of charge more. If it's going to be a metal that is going to lose electrons in that energy state, that's the orbital, we're going to call it an ion of charge plus. That is for the cases of metals. Now, in this case, fluorine, what is the valency number of electrons supposed to gain? It's 1. Now, for it to gain 1 electron, it's going to now have a complete shell. It's going to have a complete shell. So in other words, the couche de valence, maybe if I just give it a bit of a light, what you're supposed to do is, the reason why I gave the Zambian configuration electronic, it will be a bit of a guide for you when you're doing these things. The couche de valence, if we're to use the electron configuration that we learned from Zambia, it is going to be 70 for fluorine. It's going to be 70. Couche de valence, where you have the electrons that is going to allow electrons to come in, or it's going to allow electrons to go out. It's 70. That's the last energy level, isn't it?
Yes.
Isn't it for everyone? I'm saying everyone, isn't it?
Yes, it is.
Same applies to sodium. It's going to be 1 day.
Yes.
So what you do from this same thing, from this same detail I've shown you here. Therefore, the couche de valence will be the one with 7, and we'll call it 2s2 2p5. That is our couche de valence. That is for fluorine. Then for sodium, it will be 1s or 3s1, like that. Is it clear? So the couche de valence is this one here with 1 electron at the end, with just 1 electron at the end. And this one is one that occupies only 7 electrons. So your couche de valence is in other words, it's the last energy level that you're going to have for an atom. It's the last energy level that an atom is going to have. Same applies to potassium here. So from our analysis, what is the couche de valence for potassium? What is couche de valence?
4s1.
Exactly, 4s1. 4s1. Then for calcium, you people,
4s2.
man, guys, it's organic chemistry nowadays, because today's organic chemistry is fire per fire. So then this one here, you guys, sorry for working you guys early today. I have to finish Chimie Générale. Chimie Générale. Or maybe I give you the polycop you studied. So
How's design?
so that you guys rest, guys. Couche de valence. I'm also supposed to rest. Yeah. So what's the couche de valence for nitrogen? Azote. Nitrogen is called azote. Azote. That's nitrogen. So the couche de valence is
2s.
Yeah.
2p3.
Let's hope everyone saw how we're doing the couche de valence and hence the suite. Hmm?
Yes, yes, yes.
Everyone was seeing how we're doing the couche de valence and thingy. Tefio. Tefio.
Tulifia batatu muno tulemwena bonse.
Ah, wait, no. The thing is, not even knife yo. Not even knife yo. You find that this same thing I'm from teaching. I give you an element to give me configure. I've given you how many examples? Look, this is how generous I am. I've given you 1, 2, 3, 4, 5, 6. This is halfway done in the periodic table because I've done almost for each period. I've done for period 1, for period 2, for period 3, and period 4. I've done for all periods. That is being generous. When we come back in the afternoon, I'll continue with other examples. So now people will be confused. So now I'll bring in the notion of configuration électronique avec gas rare. Gas rare is what we are calling the noble gases. Now for the noble gases, it's the same thing, you people. It's the same thing. It doesn't change anything. Like it's just that the écriture is what changes. The écriture is what changes. So I'll start with the potassium. I'll start with calcium, the one that is there, like in our example, the biggest. So the calcium here, if it was going to be electron configuration avec les gaz rares, it will be. We're saying this is the couche de valence. This is the couche de valence. Tefio.
Nifio fine.
So what is 2 plus 2?
Oh,
What's 4 plus 6?
8. Oh, 12.
Guys,
Wait,
you guys need rest. And what is 2? What is that? 12 plus 2?
14,
14 plus 6.
14.
14 plus 6.
20.
Yeah? 14 plus 6. 20.
20.
Guys, have you added the correct? 2 plus 2, 4. 4 plus 2, 4 plus 8, 6. 4 plus 6. 4 plus 6.
Plus is
10.
10.
10 plus 2, 12. 12 plus 6.
12.
12 plus 6 is 18.
18. On the periodic table, which element is found at position number 18? Which element is found? You can even use my periodic table. Which one is found at position number 18? Guys, number 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. What is it called? I want you guys to sort of when I write, so know what what is it called? Number 18.
Argon.
Exactly, argon. So if you're to look at this, clearly, this one here, I will change the color. I'll change the color to yellow. The s orbital occupies a maximum of 2 electrons. Stay.
Yes.
The p orbital also occupies a maximum of 6. Steph.
Yes.
And we see this variation for the 3 energy levels. That is the 1, the 2nd, and the 3rd. It is satisfying the octet rule, the rule that I said we are supposed to have the maximum number of electrons for the shells. So the s occupies 2, the s occupies 2 here, the p occupies 6, the s also occupies 2 here, the p occupies 3 or 6. It's occupying the maximum number of electrons. Therefore, it has satisfied the octet rule. It has satisfied the octet rule. And when you calculate the number of electrons that this is going to give for all the elements that we have done, I will do all of them, then we close. You will find that it is always going to give a noble gas. It's always going to give a noble gas. And therefore, the electron configuration that we are calling the noble gas electron configuration is going to be written in this way. So the argon you are seeing here is just this thing here. This here is argon. This is argon, Jones H. The pre-Mutalese method. This is argon, Jones H. This is argon. 2 plus 2, 4. 4 plus 6, that's 10 plus 8, that's 18. And argon is at position number 18. Now, the configuration électronique d'après les gaz rares, it will be argon in brackets, like this, argon in brackets. Then you add this thing, 4s, you come and add it here. So, in other words, you've simplified this 1s, 2s, 2, 6, 3p, and you've written it as argon, and you've just added le couche de valence, which is here. So therefore, argon can be configured or can be written in this way as well. It can be written in this way. The electron configuration can be Ca20 argon 4s. Ca20 argon 4s. Then same principle applies. Is it clear for this part? Is it clear for this part?
Is it because these valence electrons can easily be lost and they can remain like argon? That's why we're writing that.
No, it's not because of, the reason is, if you have seen here, your method states we are going to look at how many electrons can be occupied by these shells, like the maximum number of electrons that can be occupied by these energy levels. And you said, I'm using your method there. I'm using your method. You said the S occupies a maximum of 2, the P occupies a maximum of 6, and the D occupies a maximum of 10. Then the, what do you call it? The other one, the F occupies a maximum of 14. If you have that kind of an arrangement in an atom, it means it has satisfied the octet rule. Now, this is what we are having here. The S, if you look at all the S energy levels, the S here, they are all occupying how many electrons? They are all occupying 2 electrons, which is the maximum, isn't it? Which is the maximum number of electrons, isn't it?
Yes.
Then the P is also occupying 6 number of electrons, which is the maximum for the P, isn't it?
Yes.
Then we know that, okay, if this is the case, if it occupies the maximum number of electrons, that is the maximum number of electrons, it therefore means that it has obeyed the octet rule, and the only elements on the periodic table that obey the octet rule are the gas rare, which are what we are calling the noble gases. Noble gases are the only ones that occupy that satisfy the octet rule. The octet rule is a rule that just justifies to say that an atom is supposed to have the maximum number of electrons, the maximum, the fullest to the highest, like the maximum number of electrons for it to like the maximum number of electrons that it's supposed to occupy for it to satisfy the octet rule. You get what I'm saying? Eh? So it is for this reason,
Yes, I get it.
yeah, it is for this reason why we are saying we are going to call it the noble gas electron configuration. Why? Because we are using noble gases, which are the only elements of the periodic table that satisfy the octet rule, to justify what the electron configuration will be at the end of the day. So when you look at this here, that's why I wanted you guys to count, because if I just came in with argon, you would have said, where is argon coming from? So the idea is, this here, the one that has satisfied the octet rule, when you calculate the number of electrons that you are supposed to have, you're going to calculate and find that it is for argon. Like argon is the configuration electronic for this here is argon. This one you're seeing here is for argon. This, what you're seeing here, is for argon. So it will be, in other words, we're going to say argon in brackets plus the 4-2. So in other words, what you've done here, you've just shortened this whole thing and you've used argon, and you've just put the couche de valence. Couche de valence. Couche de valence. If you put argon and put 1s2, s2p, 6 chan, it's wrong. It's wrong. If you put argon, you just put the couche de valence electron configuration at the end. That's all. That's what you're supposed to put. So now, with this example, is it clear? So that I go to another example. Is it clear?
No, I want to understand. So you're trying to say that if you are You're saying if we write the way argon is, let's say if you want to say write the electronic configuration for argon, we
Mhm.
can't write it the way we were writing these other ones. We have to just write
No, no,
using
no, no.
this formula.
Okay. Let me do this. Let me add another example for argon. Argon is number what? Argon is number 18. TEF. And the electron configuration Zambian is 2, 8, 8, isn't it?
Yes.
So using your method, it will be 1s, 2s, 2p, 3s, 3p, t. Now you can TEF. And we're saying the maximum is going to be 2, 2, 2, and how many? Yeah, 6. And 6 like that. 10. This is your configuration electronic. TEF for
Yes.
what?
Argon.
For argon. Now, when we are looking for the couche de valence, that's why I asked the question, say, what is the couche de valence? We say the couche de valence is the one that has the one at the extreme, like the one at the far end. This is going to be couche de valence. TEF, from what we were saying, this is our
Yes.
8, which is this here. This is our couche de valence. Now, I'm saying configuration électronique d'après les gaz rares, it will always be the couche de valence and the noble gas. So now, what noble gas is this? This one here. With 2 plus 2, that's 4, plus 8, how many is it? How many? How many?
That's 10.
10. And what's our number 10 on the noble gases? It's fluorine, nitrogen, neon, T.
Yes.
Therefore, the configuration électronique, that is for argon, it will be neon in square brackets and the couche de valence like that. So you don't put equals, you put it like that. This is for argon. You get what I'm saying now? Huh? Is it making sense now?
Yes.
Yeah. So the couche de valence you always leave it. In other words, you always leave the couche de valence. Then you will look for the noble gas. You look for the noble gas. What noble gas is it? So in the same way, this is our couche de valence. This is our couche de valence. Couche de valence. So if we want to write this in the form of the configuration électronique avec gaz rare, what is the noble gas that has only 2 electrons, or maybe say the only 2 electrons outermost here? What noble gas is that?
Helium.
Helium. So you'll be like
Helium.
helium. Then you close your brackets and you just add this couche de valence, comme ça. Is it clear?
Yes.
Then same applies to calcium, we've already done, potassium. So now the question is, what noble gas is this? So potassium and none can have the same noble gas. This is 2 plus 2, 4 plus 6, that's 10 plus 8, that's 18. It's going to be argon encore. It will be argon in square brackets. Then we should, with your couche de valence. With your couche de valence. Is it clear with this one? Is it clear? Is it clear? Then same applies to so
Yes,
sodium.
it's clear.
So
clear.
okay. So now I have to finish all the examples. So couche de valence, which one is our couche de valence? Ni T.
A.
Then what noble gas is this? This noble gas here.
Helium.
Voila. Helium. Then couche de valence. That's noble electron configuration for fluorine. Then the last one for sodium, it will be, what noble gas is this on call? Oh, sorry, this one. What noble gas is this?
Is it neon?
So it will be neon, because that gives 10 day. Then you add your terminaison. Voila, like that. You add in your terminaison. So this is the electron configuration for atoms. This is how you do electron configuration d'après règle de Kleshowski. Is it clear? Is it clear, Mtali? Is it clear?
Yes, it is. Thank you.
So Kennedy, is it clear? With electron configurations, that is with the SPDF electron configuration, with I think with this one is also this, it's also simple. It will be helium, always in square brackets, eh? In square brackets. Then you put your couche de valence there, like that. Is it clear? With all these examples we've done, I know we've not done one example, that is sulfur, but you guys will practice this. So is it clear with all these configurations that we've done? That is lithium and beryllium, potassium and fluorine and sodium, potassium, calcium, nitrogen. Is it clear? Argon, c'est clair?
Oui, c'est clair.
Cushy. Clushy. Is everything clear? Everything. From where we started, everything clear. Everything. Mutala, is it clear? From where we started, everything. Today, is it clear?
Yes, yes.
Okay.
Today it's clear. Anyway, we're just the two of us, I think, so far.
Yeah.
Everyone
Because
has
you guys are supposed to prepare for organic also, because you already have 30 minutes gone. So at exactly 10
Yeah.
hours, you guys are supposed to come in. So everything is clear. So if